Hi guys, so I'm doing this video and then one more to just kind of go over the chi-squared stuff again that we learned in class the week before spring break, because I know you've forgotten a lot of it. So just as a quick reminder, and then we'll go from there. So this first video is going to be on chi-squared goodness of fit, and I'm just going through the examples we had in class from that day, and I filled in the first couple of things. But there were two main types of chi-squared tests. Goodness of fit is when you have one categorical variable, and we're asking questions like, are the proportions for this one variable different from the claimed set of proportions? Whereas a chi-squared test of independence is looking at two categorical variables. So are these two variables associated with each other, or are the two variables dependent or independent or something like that? But that's kind of the big thing, is looking at, do we have one variable or two? So this first example, and this is the one that we actually took some data in class, if you remember, we have Mars Company claims that the distribution of colors of their mini M&Ms are distributed with the following proportions. So 13% red, 20% orange, etc. And we have these observed values from data we collected. These were numbers I made up, actually. Hold on. So yeah, these were numbers that I made up, but they were similar to the ones we collected in class. So the first thing we would always do for a goodness of fit test, I put in this extra row down here. On a test or something, you wouldn't probably get that row as a reminder, but it is a good reminder that the very first thing that we should do is figure out what would be the expected count, and that's if these proportions we were given were actually true, what would be the expected number of M&Ms we would have in each category. So what we would kind of do is, for red, it would be 0.13 times the total number, so 727 times 0.13. So what is 13% of 727, which I figured out earlier, but my phone died. About 94.5. I'm going to round all of these to one decimal place, but as always, just read carefully and round to how they tell you to round. So if I go through and do that for all of these, so this one would be 727 times 0.2, and that's 145.4. So that's always the first thing you're doing, is taking that total sample size and multiplying it by each proportion. So I'm going to go ahead and fill all these in. And the math I did earlier. Oops. And that should add up to about 727. It might be slightly off just due to rounding, but we should be dealing with the same sample size as our actual sample size. So those would be our expected counts. This is what the numbers would be if those proportions were actually exactly true. And what we're measuring with a chi-squared test is how far off or are the observed counts from these expected counts. So real quick with our hypothesis statements, the null hypothesis is that the M&M colors are the same as the claimed proportions. And then our alternate hypothesis is that the proportions of M&M colors are not the same. So null is always that things are the same, nothing's changed, nothing's different, nothing's weird. And your alternate is basically that there's some kind of change. So the colors are not proportioned the way that M&M's company says that they are. So those are hypothesis statements. Always, always, always think about those. Even if they don't ask you a direct question about it, you need to know what your hypothesis statements are, so when you write your conclusion later, you're making the right conclusion. The degrees of freedom for a chi-squared goodness of fit test is basically just the number of categories minus 1, and that is on our formula chart under the chi-squared part. Where are we at? Here we go. So chi-squared, it says DF goodness of fit is cells minus 1. So it's just the number of categories minus 1. So we have 1, 2, 3, 4, 5, 6 colors. So 6 minus 1 is 5. So that would be our degrees of freedom. And then we would go onto our chi-squared table to get the critical value, which I need to open that. So hold on. Okay, found it. So here is our chi-squared table. Again, our degrees of freedom is 5. If they don't give you a alpha or level of significance, we use 0.05. And the good thing with the chi-squared test is we will never have to split that in half. There will never be like a two-sided test like we had with the other types of tests. So I'm going to stick with 0.05, and then my degrees of freedom was 5. So my chi-squared critical value is 11.07. So that is all the setup, and now we're ready to do the actual math, which is going to be a little bit of a tricky part. So I'm going to scroll down a little bit so we can do our math, and I'm keeping the numbers up on a different screen so I know what they are, but you would want to keep those numbers handy. So to find our chi-squared statistic, our formula for chi-squared is on our formula chart. It's right here. Chi-squared equals, this E is a summation of, we do observed minus expected squared divided by expected. So basically we do this part of it for each cell, for each color of M&M, and then the summation means at the end we're going to add all those numbers together, and that total added together value is our chi-squared statistic. So for example, I would start with red, and I would write in my observed, which was 112, minus my expected, which is 94.5, squared divided by my expected, which is 94.5. And then I would continue that with all the colors all the way till I get to the last color, which is brown. Observed there was 163, minus expected, which is 94.5, squared divided by 94.5. So that could be a lot of work, just depending on how many categories you have. It could take you quite a while to individually calculate each of those things and then add them all together. So what I had shown you guys in class was a way to use your calculator to kind of cheat the system and make that whole process a lot quicker. So I'm going to remind you of that. So in your calculator, you would go to stat and then enter. And I'm just going to put my observed numbers in L1 and my expecteds in L2, and I'll come back when I've done that. So now I have typed all those numbers in. My observed are in L1, my expected are in L2. So now I'm going to use the list feature to basically do that math for me. So I'm going to go to L3, I'm going to go up to L3, so I'm highlighting L3, and this is where I'm going to type my equation basically. So I'm going to start with the parentheses, and then I want observed. Well, my observed values are in L1, so I'm going to do second one, so it says L1, minus, and then I need expected. My expected values are in L2, so I'm going to do second 2, and that gives me L2. I'm going to close parentheses, and then I'm going to say squared. So I have L1 minus L2, observed minus expected squared, and then I'm dividing by expected. So divided by, and then second 2 for L2 again, so I have observed minus expected squared over expected. So when I push enter, it's going to do that math for each row in this table. And now I have all those individual chi-squared values in L3. And the next step would be to add those all together. And I can do that by hand, like I can write all those numbers down and then just go back to my home screen and add them together, and that would be fine. But we have one more trick up our sleeve. If I do second quit to get back to my home screen, and then what I can do is use the sum feature. It is in a menu, but if you ever forget where something is, remember you can always use second 0 as the catalog, and that will give you every function in the entire calculator. So if you ever forget where something is, go to catalog and look it up there. But where the sum feature is we're going to do second stat math, and then that's where sum is. So we want number 5 for sum, and I want the sum of L3. And that is my chi-squared statistic. So when I do all of that math, if I were to individually find each of those numbers and add them all together, I get 116.8, which is a very large number. So if you remember I'm going to kind of draw this chi-squared model is kind of skewed to the right. Our chi-squared critical value was 11.07. So basically we were saying that's about as big as that chi-squared value should be if they were no different from what the claim was. If anything is bigger than that, if we get a chi-squared any bigger than that, then we're saying that's too big, those observed and expected values are too far apart, this is weird. And our chi-squared statistic was 116.8, which is well past our critical value. So our statistic was really, really, really far past our critical value. So remember, this critical value, this critical region, is our alpha, which is 0.05. The fact that we got such a really big statistic means that our p-value, which is kind of that area above our statistic, is very, very small. It's much, much smaller than the 0.05 that was our critical region. So if our statistic is in the critical region, meaning it's past the critical value, then we are rejecting our null hypothesis. Remember, our null hypothesis said that that the claimed or the actual colors of M&Ms are like what the claim was. And if we're rejecting the null, it means we say we have evidence of our alternate. So we have evidence that the proportions of M&M colors are not the same. So we're rejecting the null, we have evidence of the alternate. We have evidence that the proportions of M&M colors are not the same as what M&M's company said that it was. I'm going to write that real quick and come back. So yeah, that is our test. Goodness of fit test. I'm going to go through the other one a lot quicker, just to remind you of kind of what that would look like. So I'm going to clear this out and go down to number 2. So number 2 was one that was a little bit trickier. They don't quite word things the same. So it's commonly believed that females get in fewer accidents than males, especially with younger drivers, which is why car insurance policies tend to be less expensive for females. Doing some research, we find that 46 out of 85 randomly selected accidents involve a male driver. So that's our observed numbers. Does this give us evidence that males and females are not equally involved? So that not equally involved, we can think of that as kind of our claim. Our claim would be that they are equally involved. We're finding evidence. Is that not true? So our true proportions in this case, anytime a question is talking about like equal or is it equally spread out, our true proportions would basically be take my categories and divide them up evenly. So since we have 2 categories, my true proportions would be 0.5 and 0.5. If I had 3 categories and I'm testing about equalness, then my true proportions would be 0.33, 0.33, 0.33. If I had 4 categories and my claim was that they are equally proportioned, then my true proportions would be 0.25, 0.25, 0.25, 0.25. So we're kind of dividing it up equally. My observed counts, it said 46 of the total of 85 were males, which means math, 39? Yeah, 39 were female drivers. And my expected counts, my expected is saying that they're equally proportioned. So my expected would be that half are male and half are female, and I still want them to add up to the 85. So half of 85 is 42.5. Half of 85 is 42.5. So if it's true that they're equally involved, my expected value is that they would be equally involved. That it would be the same number for males and females. My null hypothesis would be that they are the same, that they're equally proportioned, that males and females get into the same amount of accidents. My alternate is that they are different. So down there, my alternate is that they are different, that the proportions of males and females that get into accidents are not the same. I just forgot the E in different, no big deal. So that would be our null and alternate. So then to find my degrees of freedom, I only have 2 categories. So degrees of freedom would be 2 minus 1, which is 1. And then my critical value, I'm still using 0.05 unless they tell you otherwise. So then for 1 degree of freedom, my critical value is 3.84. Oops. So chi-squared critical value is 3.84. So then to find my statistic, again, I'm going to do, for each one, observed. So for males, observed is 46, minus expected, 42.5, squared over 42.5. And then plus, for females, my observed was 39, minus my expected, 42.5, squared over 42.5. This one only has 2 categories. So 2 categories is going to make it a little bit easier to do the math. It really wouldn't take me that long to just individually figure out what these equal. So just to show you what that would look like, if I didn't feel like messing with the lists, right, I could just type in, okay, parentheses, 46 minus 42.5 squared divided by 42.5. Boom, there's my value for males. Same thing for females. Parentheses 39 minus 42.5, close parentheses, squared,